Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. Let yourself settle. There is nowhere to go, nothing you need to calculate, nothing you need to solve. For now, you are simply here, breathing, aware, and quietly curious. Tonight, we will consider something so familiar that it almost disappears beneath notice: time. It seems simple, it seems obedient. It ticks on the wall, it glows on the corner of a screen, it moves the hands of a clock in smooth circles, it marks the rhythm of your day. Morning becomes afternoon. Afternoon becomes evening, and evening softens into night. Time feels like a current, something that flows past you, carrying memory behind and possibility ahead. We speak of time as though it were a river. We say it passes, we say we spend it, we say we are running out of it. But what if that language is not quite right? What if time does not flow at all? What if time is not a current, but a structure, a geometry, something far quieter, far more still? In daily life, time feels uniform. If 1 second passes for you, it passes for everyone else. If a minute stretches long in boredom, it stretches the same for the world beyond your thoughts. Clocks appear synchronized, the world appears coordinated, schedules align, meetings begin, trains depart, aging unfolds gradually and predictably. You grow older, planets orbit, stars rise and set, and through it all, time feels steady, reliable, impartial. It seems to move forward everywhere, at the same pace. For all observers, this assumption feels so natural, so unquestioned, that it hardly seems like an assumption at all. For centuries, scientists believed exactly this. Time was treated as a background, a universal ticking, an invisible metronome keeping rhythm for the entire cosmos. The laws of motion were written using time as a constant, a parameter that flowed identically for all. It was not debated, it was not doubted, it was simply there, an unquestioned foundation. And yet, at the beginning of the 20th century, something subtle shifted. Not dramatically, not explosively, but quietly. A young patent clerk in Switzerland began asking careful questions. His name was Albert Einstein. He was not surrounded by laboratory equipment. He did not command a grand observatory. He worked among technical drawings and patent applications, examining devices, evaluating mechanisms, thinking deeply, slowly, persistently. He was fascinated by light, by how it moved, by how it behaved, and by what would happen if one tried to chase it. The questions he asked were deceptively simple. If you move alongside a beam of light, does it appear frozen beside you? If you measure its speed while running toward it, does it slow down relative to you? Classical physics suggested that motion should add and subtract, like velocities on a calm road. If you walk forward inside a moving train, your speed relative to the ground increases. If you walk backward, it decreases. This logic seemed universal, but experiments were beginning to show something strange. The speed of light did not seem to change. No matter how fast the observer moved, it remained constant, a fixed number, not dependent on direction, not dependent on speed, not dependent on perspective. This was unsettling, because if light's speed never changes, then something else must give, and that something was time. Einstein realized that to preserve the constancy of light's speed, the structure of time itself must adjust. Seconds could stretch, moments could compress. Events that appeared simultaneous to one observer might not be simultaneous to another. This was not a minor correction. It was a redefinition. Time was no longer universal. It became relational, dependent on motion, dependent on position, dependent on gravity. The steady ticking background dissolved, and in its place emerged something geometric, something woven together with space. We call it spacetime, a single four-dimensional structure where time is not separate from space, but intertwined with it. In this structure, every event has coordinates, not just where, but when. and the separation between events depends on the observer's state of motion. This realization did not arrive with thunder. It arrived with clarity, with equations written carefully, with thought experiments imagined patiently. Einstein did not shout that time was broken. He showed, quietly, that our intuition had been incomplete. Time was not abolished. It was refined, deepened, made more subtle. As we move gently through this exploration, there is no need to hold every detail tightly. There is no need to calculate transformations or memorize principles. Instead, allow the ideas to unfold slowly, like pages turning in calm succession. You already experience time. You already sense its passage. Now we will examine whether that sensation reflects the fundamental structure of reality or whether it reflects the architecture of the mind. In the coming reflections, we will move carefully from the familiar to the surprising, from the steady ticking clock to the flexible geometry of space-time, from the idea that time flows to the possibility that it simply exists. Rest in the understanding that this is not a story of chaos, it is not a story of confusion. It is a story of precision, of careful reasoning, of mathematical elegance, of a universe that is not less stable than we imagined, but more intricate, more structured, more quietly astonishing. The revolution was not loud. It did not shatter the cosmos. It reshaped our description of it. Time did not disappear. It transformed. It became something that bends, something that depends, something that may not flow at all. For now, let that possibility rest gently in your thoughts. Time may not be a river. It may be a landscape, and you are not drifting helplessly through it. You may be tracing a path within it, calmly, inevitably, precisely. There will be no rush tonight, no urgency, only the steady unfolding of ideas, one careful insight at a time. As we begin, hold on to this simple awareness. The seconds you feel, the minutes you measure, the years you remember, may not be the fundamental fabric of reality. They may be something softer, something constructed, something emerging from deeper geometry. And in recognizing that, there is no danger, only wonder, a quiet revolution, still echoing in every ticking clock for centuries. Time was simple, not in poetry, not in feeling, but in physics. In the great structure of classical mechanics, time was absolute. It flowed identically everywhere, without hesitation, without variation, without regard for who was watching. In the late 17th century, Isaac Newton described a universe governed by precise mathematical laws. Objects moved according to forces. Planets orbited according to gravity. Projectiles traced elegant arcs through the air. And beneath all of this motion, time advanced, steadily, uniformly. Newton wrote of absolute time as something that flows equably, without relation to anything external. It was not influenced by matter. It was not altered by motion. It did not bend. It did not stretch. It did not hesitate. It simply was, a universal ticking shared by all observers. If two clocks were built carefully and synchronized at the beginning, they would remain synchronized forever, no matter where they were carried, no matter how fast they traveled. Time was the same in London and in distant seas, the same on Earth and among the stars. The idea was clean, elegant, comforting. Space, too, was absolute. It existed as a vast, unmoving stage, an infinite container within which matter moved. Events unfolded upon this stage, but the stage itself did not participate. It did not react. It did not deform. It was a silent arena, unchanging. Time and space were the background. Matter and motion were the actors, and the script was written in differential equations. This worldview worked extraordinarily well. With Newton's laws, one could predict the motion of falling objects, the trajectories of cannonballs, the timing of eclipses, the return of comets, the behavior of tides, the stability of planetary orbits. It was not merely approximate, it was astonishingly precise. The planets moved almost exactly as predicted, year after year, century after century. Astronomers refined their measurements, and the equations held. The solar system became a clockwork mechanism, a grand celestial machine. Planets orbiting in ellipses, moons circling their hosts, gravitational attraction described by a simple inverse square law. The farther apart two masses were, the weaker their attraction, proportional to 1 divided by the square of the distance. This relationship explained the motions of the heavens with calm mathematical certainty. Because the predictions were so successful, confidence in absolute time grew stronger. It seemed beyond question. After all, if time were variable, If seconds stretched unpredictably, the equations would fail, planetary motion would drift from prediction, clocks would fall out of alignment. But none of this occurred. The cosmos appeared disciplined, regular, obedient to precise law. Classical mechanics treated time as a parameter, a variable often labeled with a single letter. It entered equations smoothly. Position as a function of time, velocity as the rate of change of position with respect to time, acceleration as the rate of change of velocity with respect to time. Time was the independent variable. Everything else depended on it, but it depended on nothing. It was not influenced by forces. It did not respond to energy. It was a universal reference, shared by all observers. Two events separated by 1 second were separated by 1 second for everyone. Simultaneity was universal. If lightning struck two distant hills at the same moment, then it struck them simultaneously for every observer. Whether standing between the hills or watching from a distant mountain, there was one present, one shared now, extending across the universe. Like an invisible sheet, this intuition runs deep. Even today, it feels obvious that there is a single present moment. That right now, across distant galaxies, there exists one universal slice of time, a shared cosmic instant. It feels intuitive because our senses evolved within slow motion. Relative to the speed of light, our everyday velocities are tiny, negligible compared to the speed at which light travels. So tiny that any deviation in time caused by motion would be imperceptible. The world of daily life reinforces the illusion of uniformity. If two people set their watches in the same room and walk in different directions at ordinary speeds, they return with watches still synchronized. Nothing appears distorted. Nothing seems altered. The small differences that do occur are so minute that without precise instruments, they remain invisible. So intuition aligns with classical theory, and classical theory aligns with observation, at least within the limits of human experience. This is why absolute time feels natural, because in the realm of everyday motion, it is an excellent approximation. It simplifies calculations, it stabilizes expectations, it provides a clean framework. And within that framework, the universe appears predictable. Causality flows in a single direction. Past influences present, present influences future, but never the reverse. Time becomes a line, extending indefinitely backward and indefinitely forward. The past fixed, the future open, the present advancing, steadily, unstoppably. Even philosophers largely accepted this structure. Debates about time focused on perception or metaphysics, but the physical foundation seemed secure. The laws of motion did not require revision. The celestial predictions did not falter. The stage remained firm. But beneath this stability, there were quiet questions, small inconsistencies, hints that perhaps the stage was not as rigid as it appeared. At first, these hints did not challenge the foundation. They seemed like technical complications, minor puzzles to be solved within the existing framework. No one suspected that time itself would become the subject of revision, because absolute time was not merely a detail, it was the backbone of mechanics. To question it was to question the entire structure of classical physics. And yet, as the 19th century progressed, new phenomena emerged. Electricity and magnetism revealed patterns that did not fit neatly into Newton's framework. Equations describing electromagnetic waves predicted a specific speed, a speed that appeared fixed, independent of the motion of the source, independent of the motion of the observer. This was strange, because in classical reasoning, velocities add and subtract. But here, the equations suggested constancy. At first, physicists attempted to preserve the familiar structure. They proposed that light moved through an invisible medium, a substance filling all of space, called the ether. If space was a stage, then the ether was the air within that stage, through which light waves propagated. And if Earth moved through this ether, there should be a detectable difference in light speed. Depending on direction, careful experiments were designed. Interferometers constructed with delicate precision, beams of light split and recombined, measured for tiny shifts, but the results were puzzling. No matter how the apparatus was rotated, no matter the time of year, no matter Earth's motion around the sun, the expected variation was absent. Light speed appeared the same, in all directions, to a remarkable degree of accuracy. This null result was unsettling, but at first it was treated as a complication. Perhaps the ether dragged along with Earth, Perhaps measuring instruments contracted slightly. Perhaps some subtle effect masked the expected change. The commitment to absolute time remained strong, because abandoning it would require rethinking space, motion, simultaneity, causality itself. And so the classical worldview held firm, stable, trusted. It had earned that trust through centuries of success, and for the motions of planets, the trajectories of projectiles, the engineering of bridges, it remained profoundly effective. Even today, engineers use Newtonian mechanics routinely because at everyday speeds and ordinary gravitational fields, it works beautifully. Absolute time continues to function as an excellent approximation, which is why the revolution that followed was not a rejection, but a refinement, not a destruction, but a deepening. The comfort of absolute time was not foolish, it was incomplete. It described a limited domain with elegance, but the universe extends beyond ordinary domains, beyond everyday velocities, beyond gentle gravitational fields. And when those extremes are explored, the stage begins to bend, the ticking begins to stretch, the universal present begins to fragment. For now, rest in the stability of this classical picture. Feel how natural it seems, a steady river of time, flowing uniformly everywhere, a vast stage of space, unmoving, infinite, and within it, planets orbiting, objects falling, clocks ticking, all in synchrony. It is a powerful vision, one that shaped centuries of science, and it is from this calm foundation that the quiet revolution will emerge. But for this moment, remain with the comfort, the order, the elegant simplicity of absolute time, unquestioned, unstretched, unbent, steady and serene. As the 19th century unfolded, electricity and magnetism were no longer curiosities. They were becoming unified, carefully measured, mathematically described. James Clerk Maxwell gathered the known laws of electricity and magnetism and expressed them as a set of equations, elegant, compact, powerful. These equations did something extraordinary. When combined, they predicted the existence of waves, self-propagating disturbances in electric and magnetic fields, traveling through space at a specific speed. That speed was not arbitrary. It emerged directly from measurable constants, the electric constant and the magnetic constant. When Maxwell calculated the speed implied by his equations, it matched the measured speed of light. Light was an electromagnetic wave. This realization unified optics with electromagnetism, a profound achievement. But hidden within it was a quiet tension. Maxwell's equations predicted one speed for light, a fixed number, not dependent on the motion of the source, not dependent on the motion of the observer. This was unusual. In classical mechanics, velocities combine. If a boat moves forward in a river, its speed relative to the shore depends on both the boat's speed through the water and the river's current. If you throw a ball forward while riding in a carriage, its speed relative to the ground is the speed of the carriage plus the speed of your throw. This addition of velocities felt universal, natural, almost inevitable. So when Maxwell's equations implied that light travels at a single fixed speed, physicists sought to preserve classical intuition. They proposed that light must travel through a medium, just as sound travels through air. Water waves travel through water. This invisible medium was called the luminiferous ether. It was imagined as filling all of space, subtle, transparent, undetectable by ordinary means, but necessary. If light were a wave, it must wave in something. And if Earth moved through this ether as it orbited the Sun, then there should be a detectable difference in light's speed. Depending on direction, light traveling in the direction of Earth's motion should differ slightly from light traveling perpendicular to that motion. This was not speculation alone, it was testable. Albert Michelson and Edward Morley designed a precise experiment. Using an instrument called an interferometer, a beam of light was split into two perpendicular paths, reflected back, and recombined. If one beam traveled slightly faster or slower than the other, due to Earth's motion through the ether, the recombined beams would produce a shifting interference pattern. Tiny differences would become visible. The apparatus was rotated, measured carefully, repeated across seasons as Earth moved around the Sun, but no shift appeared. Within the sensitivity of the experiment, there was no detectable ether wind, no variation in light's speed. The result was null, not dramatic, not explosive, but deeply unsettling. If Earth moved through the ether, why was no motion detected? Some physicists propose that objects contract slightly in the direction of motion, by just enough to cancel the expected difference. This contraction would occur automatically, silently, perfectly, ensuring the experiment always returned a null result. It was a clever hypothesis, but it felt contrived, a mathematical adjustment designed to preserve a deeper assumption, the assumption of absolute time. Because if time were universal and space were fixed, then something else must adjust to explain the constancy of light speed. Yet the tension grew. Maxwell's equations did not require an ether. They described waves in electromagnetic fields themselves. Perhaps light did not need a material medium at all. But even if the ether were discarded, the constancy of light speed remained puzzling. If you move toward a light source, classical intuition suggests you should measure the light as approaching faster. If you move away, it should approach more slowly. But experiments suggested otherwise. The measured speed remained constant. Regardless of the motion of the observer, this implied that the traditional addition of velocities might not apply to light. And if the addition of velocities fails, then the underlying structure of space and time must be reconsidered. The difficulty was subtle, because everyday experience did not reveal the problem. At ordinary speeds, much slower than the speed of light, the differences are minuscule, too small to notice without extraordinary precision. So classical mechanics remained effective in daily life. Bridges stood, cannons fired, planets orbited. But beneath this success, there was growing tension at the foundations. Two pillars of physics, Newtonian mechanics and Maxwell's electromagnetism, did not fit together cleanly. One assumed absolute time, the other implied a universal speed of light. And those assumptions could not both be strictly true. Physicists at the turn of the century were aware of this, but the resolution was not obvious. To alter Maxwell's equations would discard a theory of extraordinary predictive power. To alter Newtonian mechanics would challenge centuries of confidence. The conflict was quiet, mathematical, subtle, but profound. Something fundamental was misaligned. The universe was not inconsistent, but our descriptions of it were, and so the stage was set for a different approach, not one that added complexity, but one that questioned the hidden assumption that time must be the same for all observers. The solution would not involve restoring the ether, nor introducing elaborate compensations. It would involve accepting that the speed of light truly is constant, and allowing space and time themselves to adjust. This adjustment would not be arbitrary. It would be governed by precise mathematical transformations, linking measurements between observers in relative motion. But to arrive there, one had to let go of the comfort of absolute simultaneity and absolute time. The constancy of light speed was not merely a curious detail. It was a boundary, a limit. No material object could exceed it. No signal could travel faster. It defined the maximum speed of causal influence. This was more than a property of light. It was a structural feature of reality, a conversion factor between space and time, measured in units of distance per unit of duration. It connected how far something travels with how long it takes. In a way that is the same for all observers, if that speed is invariant, then observers moving relative to one another must disagree about lengths, about durations, about simultaneity, but agree on the speed of light. This is where the tension becomes clarity. The failure to detect the ether was not a failed experiment. It was a signpost, pointing away from classical assumptions and toward a new structure, one in which time is no longer absolute, but interwoven with motion. The growing tension at the dawn of the 20th century was not chaos, it was alignment. The pieces were preparing to rearrange. The equations were waiting for reinterpretation. The null result was not empty, it was instructive. Something fundamental was wrong with the assumption that time flows identically everywhere, and in that quiet inconsistency, a revolution began to form, not through loud proclamation, but through careful thought, slow reasoning, and the willingness to question what felt obvious. Time, once assumed universal, was about to become relational. But that realization would emerge step by step, from simple postulates, applied with uncompromising logic, until the structure of reality revealed itself in a new light. For now, let the tension rest gently. Two successful theories, not yet reconciled, a constant speed of light, a missing ether, and a quiet sense that something fundamental must change. In the year 1905, a young physicist published a paper with a quiet title on the electrodynamics of moving bodies. There were no dramatic claims, no declarations of revolution, only two simple postulates, two statements so restrained that their consequences were almost invisible at first glance. The first postulate was this: the laws of physics are the same in all inertial frames of reference. An inertial frame is one that moves at constant velocity, not accelerating, not rotating, simply gliding smoothly. If you are inside a train moving at constant speed and you perform an experiment, the results will be identical to those obtained in a laboratory at rest. No mechanical experiment can reveal whether you are moving uniformly. This principle was not new. It echoes Galileo's insight centuries earlier. If you drop a ball inside a smoothly moving ship, it falls straight down, not backward. Uniform motion cannot be detected from within. This principle preserves the symmetry of physics. No inertial observer is privileged. No stationary frame is absolute. The second postulate was more daring. The speed of light in vacuum is the same for all observers, regardless of the motion of the source, regardless of the motion of the observer. This was the statement that required courage, because it directly contradicted classical intuition. If you move toward a beam of light, you do not measure it as approaching faster. If you move away, you do not measure it as approaching slower. Its speed remains constant. Approximately 300,000 kilometers per second, or about 186,000 miles per second, a fixed cosmic limit. These two postulates together are deceptively simple, but when applied with strict logic, they reshape space and time. To understand how, consider a thought experiment. Imagine a long train moving smoothly along a straight track at constant speed. Inside the train sits an observer at its midpoint, standing on the platform outside. Another observer watches the train pass. Now imagine lightning striking both ends of the train. One strike at the front, one strike at the back. For the observer standing on the platform, if the light from both strikes reaches him at the same instant and he is equidistant from the points of impact, he concludes the strikes were simultaneous. They occurred at the same time. Now consider the observer inside the train. She is moving forward with the train. As the lightning strikes occur, she moves toward the flash from the front and away from the flash from the back. If the speed of light is constant for her as well, then the light from the front strike has a shorter distance to travel to reach her, while the light from the rear strike has a longer distance to travel. She will see the flash from the front first and the flash from the back later. From her perspective, the lightning did not strike simultaneously. One strike occurred before the other. Neither observer is mistaken, neither perception is flawed. Each is applying the same physical laws, each measures the same speed of light, yet they disagree about simultaneity. This is the breakdown of universal now. Simultaneity depends on motion. Two events that are simultaneous in one frame may not be simultaneous in another. The concept of a single present moment extending across space begins to dissolve. If observers moving relative to one another cannot agree on which events occur at the same time, then the idea of a universal present loses meaning. Time becomes interwoven with space. To preserve the constancy of light speed, durations must adjust, lengths must adjust, and simultaneity must become relative. Einstein did not begin by modifying time directly. He began by insisting on the equality of physical laws and the constancy of light speed. From those assumptions, the transformations emerge naturally, mathematically precise, unavoidable. Coordinates of space and time for one observer are related to those of another through what are now called Lorentz transformations. These transformations ensure that the speed of light remains constant. Even though observers measure different durations and lengths, this is not an illusion, not a trick of perception. It is embedded in the structure of measurement itself. Clocks moving relative to an observer tick differently. Rods aligned with motion contract slightly. But these are not mechanical distortions. They are consequences of how space and time relate. The radical simplicity of Einstein's approach lies in its restraint. He did not invent elaborate mechanisms. He did not add hidden forces. He removed assumptions. He allowed the postulates to guide the geometry, and the geometry reshaped intuition. The disagreement about simultaneity is not a paradox to be resolved. it is a feature to be accepted. There is no absolute frame that determines the true ordering of distant simultaneous events, only relations between observers, only transformations linking their measurements. Time is no longer universal, it is local, tied to the observer's state of motion, yet causality remains intact. If one event can influence another, if a signal traveling at or below the speed of light connects them, all observers will agree on their causal order. Relativity does not permit contradictions. It does not allow effects to precede causes within any frame. It refines the structure of influence. By placing a limit on how fast information can travel, the constancy of light speed is not merely a property of light, it is the boundary of causality, a maximum rate at which cause can affect effect. This limit shapes the structure of time itself. When two events are separated by more space than light can traverse in the time between them, their temporal order may differ for different observers. But if one lies within the light signal reach of the other, their ordering is fixed. The geometry enforces consistency. Thus, from two quiet postulates, the familiar structure of absolute time dissolves. In its place arises a framework where time and space depend on motion, where simultaneity is relative, where the present is not universal, and yet the laws remain symmetrical, observers remain equal, physics retains coherence. The revolution is not destructive, it is clarifying. Time is not discarded, it is redefined, not as a flowing river shared by all, but as a coordinate intertwined with space, measured differently by observers in motion. The simplicity of the postulates hides their depth. They are not complicated statements, they are statements of symmetry, of invariance. Of equality, from them unfolds a new understanding, one in which the steady ticking of absolute time is replaced by a flexible geometry, quietly consistent, universally binding, and profoundly different from what intuition once suggested. Here, the quiet revolution becomes visible, not in noise, but in logic, not in spectacle, but in clarity. Time is no longer what it seemed, and yet the universe remains ordered, precise, and serene. When the constancy of the speed of light is accepted, and the principle of relativity is preserved, the consequences unfold with mathematical precision. One of the first consequences is time dilation, the slowing of time due to motion. To see how this arises, imagine a simple clock, not one with gears, not one with springs, but a clock made of light, two mirrors facing each other. With a pulse of light bouncing between them, each round trip of the light pulse marks one tick. In the rest frame of the clock, the light travels straight up, reflects, and travels straight down. The distance between mirrors remains constant, and the time between ticks is fixed. Now imagine that this clock is placed aboard a spacecraft, moving smoothly at high speed relative to an outside observer. From the perspective of the spacecraft, nothing changes. The light still moves straight up and down. Between the mirrors, each tick occurs as usual, but from the perspective of the observer watching the spacecraft pass by, the light no longer travels straight up and down. Because while the light moves between the mirrors, the spacecraft moves horizontally. The light traces a diagonal path, upward and forward, then downward and forward. The path is longer, not because the mirrors changed, but because the frame of reference changed. And because the speed of light is constant for both observers, the light must travel that longer diagonal path at the same speed. If the path is longer and the speed is fixed, then the time between ticks must increase. The moving clock ticks more slowly. From the perspective of the stationary observer, this is not mechanical delay, it is not friction, it is geometry. The structure of spacetime demands it. The mathematical relationship that describes this effect involves a factor dependent on velocity relative to the speed of light. As velocity increases, the factor grows larger, and time dilation becomes more pronounced. At everyday speeds, such as walking, driving, even flying in an aircraft, the effect is extraordinarily small, far beyond direct perception, but at speeds approaching the speed of light, the effect becomes dramatic. Seconds stretch, durations lengthen. A clock moving at high speed accumulates less time than one at rest. This is not hypothetical, it has been tested repeatedly. One of the earliest confirmations involved subatomic particles called muons. Muons are unstable particles created when cosmic rays strike Earth's atmosphere. At rest, a muon decays in about 2 millionths of a second. That duration is so brief that even traveling near the speed of light, it should not reach Earth's surface from high in the atmosphere. It should decay long before arriving. And yet, muons are detected at ground level, in numbers far greater than classical reasoning would predict. The explanation is time dilation. From the perspective of observers on Earth, the muons are moving at speeds close to that of light. Their internal clocks tick more slowly. They experience less time before decaying, and thus survive the journey to the surface. Particle accelerators provide even clearer confirmation. When particles are accelerated to velocities extremely close to the speed of light, their lifetimes increase dramatically. In precise agreement with the predictions of special relativity, the effect is not approximate. It matches calculation to remarkable accuracy. Time dilation is not philosophical. It is measurable, operational, integrated into modern technology. Even the global positioning system, which relies on satellites orbiting Earth, must account for relativistic time effects. Satellites move at thousands of kilometers per hour and orbit in weaker gravitational fields than those on Earth's surface. Both motion and gravity influence their onboard clocks. If these effects were ignored, positioning errors would accumulate rapidly. Within a single day, the system would drift by kilometers. But the corrections are built in, calculated carefully, applied continuously. Time dilation is not abstract. It guides navigation, synchronizes networks, shapes the functioning of modern infrastructure. The concept of proper time becomes central here. Proper time is the time measured along the path of an object. By a clock moving with it, it is the time experienced locally. For any observer, their own proper time always advances normally. Their own heartbeat feels steady. Their own clock ticks regularly. It is only when comparing different world lines, different paths through space-time, that differences in elapsed time emerge. This leads naturally to what is often called the twin paradox. Imagine two twins. One remains on Earth. The other travels in a spacecraft at very high speed, journeying to a distant star and returning. According to special relativity, the traveling twin's clock runs more slowly during the journey. Upon reunion, the traveling twin is younger, not by illusion, but by measurable difference in elapsed proper time. The situation may seem symmetrical at first glance. Each twin sees the other in motion. Why should one age less? The resolution lies in the fact that the traveling twin changes frames, accelerating during departure, turning around, decelerating upon return. The stay-at-home twin remains in a single inertial frame. The paths through space-time are not symmetrical. Their world lines differ, and the geometry determines the proper time accumulated along each path. Time is not universal. It depends on the trajectory through space-time. Motion alters duration, not by force, not by distortion of mechanism, but by the structure of space-time itself. This realization reshapes intuition profoundly. Time is not a single universal river. It is a coordinate intertwined with space, and the path you trace through that geometry determines how much time you experience. At low velocities, the effects are negligible. Time dilation becomes noticeable only when velocity approaches a significant fraction of the speed of light. But the principle holds at all speeds. Even now, as you sit quietly, you are moving with Earth as it rotates and orbits the Sun and moves within the galaxy. Each motion contributes infinitesimal adjustments to elapsed time, too small to feel, but real, measured, confirmed. Time stretches, time compresses. Depending on motion, the steady ticking of classical physics dissolves into something dynamic, yet not chaotic, ordered by precise transformation, bound by the invariant speed of light. This is not a breakdown of causality. It is a refinement of measurement. Each observer carries their own time, linked to their state of motion. And when observers compare clocks, they discover that time is not shared universally, but accumulated along paths. This is the quiet consequence of Einstein's postulates. Not dramatic, not destructive, but transformative. Time no longer stands outside motion. It participates, it responds, it is woven into the geometry of the universe. And through that geometry, it reveals its flexibility, calmly, inevitably, precisely. If motion changes duration, then it must also change distance. Because space and time are no longer separate arenas, they are intertwined, linked by the invariant speed of light. To preserve that invariance, lengths measured along the direction of motion must contract, not by mechanical pressure, not by compression of atoms, but by geometry. Imagine again a spacecraft moving at high velocity relative to an outside observer. Inside the spacecraft, a rigid rod lies aligned with the direction of motion. An observer traveling with the spacecraft measures the rod's length, using rulers at rest relative to it, and obtains a certain value. Call this its proper length. Now consider the measurement made by an observer watching the spacecraft pass by. To measure the rod's length, the outside observer must determine the positions of both ends at the same moment in their frame of reference. But because simultaneity is relative, the definition of at the same moment differs between observers. The outside observer finds that the rod's length, measured in their frame, is shorter than its proper length. This effect is known as length contraction. It occurs only along the direction of relative motion. Perpendicular dimensions remain unchanged. The faster the relative velocity, the stronger the contraction. Approaching the speed of light, the contraction becomes significant. Yet within the spacecraft, no one perceives compression, no stress, no strain, because all measuring instruments within that frame contract equally. Everything remains proportionally consistent. Length contraction and time dilation are not separate phenomena. They are two aspects of a single transformation. Linking space and time between observers, the Lorentz transformations express this relationship precisely. They show how coordinates of space and time shift between inertial frames moving relative to one another. Distance and duration are not absolute quantities. They depend on the observer's state of motion. But there is something that remains invariant, a quantity that does not change: the spacetime interval. Consider two events, separated in space and time. Different observers may disagree about the distance between them. They may disagree about the time elapsed. But when space and time are combined in a particular mathematical form, the resulting interval remains the same for all inertial observers. This interval is calculated by taking the time separation, multiplying it by the speed of light, squaring that product, then subtracting the square of the spatial separation. The result is invariant, unchanged by transformation. This invariant interval reveals something profound. Space and time are not independent. They form a unified four-dimensional structure. Hermann Minkowski, a mathematician and former teacher of Einstein, recognized this geometric unity clearly. He described space and time as a single entity, space-time. In this four-dimensional geometry, an event is specified not only by three spatial coordinates, length, width, height, but also by a temporal coordinate, a moment. Each object traces a path through this space-time. That path is called a world line. A stationary object from a given frame traces a vertical world line, advancing through time without changing spatial position. An object moving at constant velocity traces a tilted world line, advancing through time while changing position in space. In this view, motion through space is inseparable from motion through time. All objects move through space-time. Even those at rest in space, they move forward in time, at a rate determined by the geometry. If an object increases its velocity through space, its motion through time decreases correspondingly. This is time dilation expressed geometrically. The total space-time interval remains constant, but its components, spatial and temporal, adjust. One increases, the other decreases. This is why motion can be described as a kind of rotation in space-time. Not rotation in ordinary three-dimensional space, but rotation in four-dimensional geometry. When an object changes velocity, it changes the orientation of its world line. More motion through space means less motion through time. The geometry enforces this balance. The invariant interval is analogous to the distance between 2 points, but measured in space-time, not in ordinary space. Just as the distance between 2 points on a plane is independent of how one rotates coordinate axes, the space-time interval is independent of inertial frame. This geometric insight replaces intuition. In classical physics, time was a separate parameter, flowing uniformly. Space was an independent stage. In special relativity, they are merged, interdependent, unified by invariant structure. This unification resolves the tension between Maxwell's equations and classical mechanics. The speed of light remains constant. Because it is woven into the geometry itself, it is not merely the speed of a particular phenomenon, it is the conversion factor between space and time, a fundamental constant of space-time. When this is accepted, The apparent distortions of length and duration are not distortions at all. They are projections. Different slices through the same four-dimensional structure. Each observer defines simultaneity differently, and therefore slices space-time differently, but the underlying structure remains consistent. This geometric interpretation brings calm clarity. There is no contradiction, no paradox, only perspective. Observers in relative motion describe events differently, but agree on invariant quantities. The universe is not fragmented, it is unified at a deeper level. The replacement of intuition by geometry may feel abstract, but it is precise, testable, mathematically elegant. Experiments confirm length contraction indirectly through the behavior of particles at high velocity, through consistency of electromagnetic theory, through the functioning of accelerators and detectors. The geometry holds, the predictions align with observation. Time becomes one dimension among four, not flowing independently, but forming part of a larger structure. In this view, the present is not a universal slice. It is a frame-dependent cross-section of space-time. Different observers, moving differently, carve different presents from the same four-dimensional fabric, and yet the fabric itself remains coherent, stable, consistent. The idea that motion is rotation in space-time invites a subtle shift in perception. Instead of imagining objects moving through a separate time, imagine them tracing lines through a geometric continuum, their world lines extending from birth to cessation. Every moment part of that path. The geometry does not flow, it simply is. What we perceive as passage may arise from our movement along our world line, from one event to the next. The unification of space and time is not a poetic metaphor. It is encoded in equations, verified in laboratories, embedded in technology. It replaces the rigid stage of classical physics with a dynamic yet orderly continuum. And in that continuum, time loses its independence, becoming inseparable from space, becoming geometry quietly, elegantly, inevitably. When space and time are unified, and when different observers slice space-time differently, the idea of a universal present dissolves. What remains is relativity of simultaneity, the recognition that now is not absolute but frame-dependent. To understand this more deeply, imagine space-time as a vast four-dimensional continuum, each event marked by 3 spatial coordinates and 1 temporal coordinate. An observer defines their present moment. By selecting all events they consider simultaneous. In classical physics, this selection is simple. All observers agree there is one horizontal slice, one universal layer of now, extending across space, but in special relativity, different observers in motion tilt that slice. Each inertial frame defines simultaneity differently. 2 observers moving relative to one another will not agree on which distant events occur at the same time. This is not confusion, it is geometry. Consider again 2 distant events, separated in space. If they cannot influence each other, because light does not have enough time to travel between them, then their temporal order may differ between observers. One observer may say event A occurred before event B, another may say event B occurred before event A, and neither is incorrect, because no causal connection exists between them. Relativity does not permit contradictions in cause and effect. It protects causality by limiting influence to the speed of light. To visualize this, physicists use the concept of light cones. At any given event in space-time, one can imagine a cone extending forward in time, representing all possible events that could be influenced by that event. Through signals traveling at or below the speed of light, this is the future light cone. Similarly, a cone extends backward in time, representing all events that could have influenced the current event. This is the past light cone. Events inside these cones are causally connected. Their order is fixed, agreed upon by all observers, but events outside these cones, in what is called the space-like region, cannot influence one another, and their temporal order may vary depending on the observer's motion. This geometric structure ensures consistency. No observer will ever see an effect precede its cause. Because cause and effect lie within each other's light cones, the speed of light defines the boundary, the maximum rate at which information can travel. Within this structure, simultaneity becomes local, not global. An observer defines now only for events at their location. Extending simultaneity across distance requires convention, and that convention depends on frame. In everyday life, because relative velocities are small, The differences in simultaneity are negligible. Two clocks synchronized carefully remain effectively synchronized for practical purposes. But at high velocities, the disagreement becomes measurable. This has been confirmed experimentally. Through precise synchronization of atomic clocks, transported at high speeds or placed in different inertial frames, they accumulate time differently, and events considered simultaneous in one frame shift slightly in another. The breakdown of shared present is not chaos, it is structure. Observers moving relative to one another define different coordinate grids over spacetime, each grid consistent internally, but rotated relative to others. Just as two observers rotated relative to one another in space disagree about which directions are horizontal and vertical, observers moving relative in spacetime disagree about which events are simultaneous, yet the invariant interval remains unchanged. The geometry remains intact, causality remains preserved. The relativity of simultaneity challenges intuition. Because human perception evolved within narrow conditions, velocities much smaller than the speed of light. Gravitational fields weak, spatial separations modest. Under those conditions, differences in simultaneity are too small to detect. The present appears universal, but at cosmic scales, or near light speeds, the tilt becomes significant. Imagine two observers passing each other at high velocity. Each constructs their own plane of simultaneity, a set of events considered to occur now. Those planes are not parallel, they intersect differently with distant world lines. For one observer, a distant star may have already emitted a pulse. For the other, that emission lies in the future. Neither view is privileged, both are valid within their frame. This does not imply that the future is mutable, or that causality is violated. Only that the labeling of distant events as past, present, or future depends on motion. Time ordering within light cones remains invariant, but outside them, order becomes relative. The collapse of universal now is one of the most profound implications of relativity. It suggests that the present moment is not a global feature of the universe, but a local perspective. Your present is defined along your world line, your immediate event in spacetime. Extending that present across the cosmos requires selecting a slice, and that slice depends on your state of motion. This insight prepares the ground for deeper reflection. If there is no universal present, if different observers disagree about which distant events are happening now, then perhaps the division between past, present, and future is not built into the fabric of reality, but emerges from perspective. The geometry of spacetime does not privilege one slice over another. All events exist within the four-dimensional continuum, connected by invariant structure, separated by intervals, organized by light cones, but not divided by a single advancing moment. This realization is not unsettling, it is clarifying. It reveals that our experience of flow may be distinct from the underlying geometry. The relativity of simultaneity does not eliminate time, it refines it, replacing a universal present with a network of local perspectives, bound together by invariant laws, causality constrained by the speed of light, temporal ordering preserved within light cones, and flexible beyond them. In this structure, time becomes part of geometry, not an external river, but a dimension woven into the continuum, and each observer traces their own path, defining their own present. Within the same coherent fabric, precise, consistent, and quietly profound, until now, motion alone has shaped our understanding of time. But gravity also participates, not as a force pulling objects through space alone, but as curvature in spacetime itself. Einstein's next insight emerged from a simple question: what would it feel like to fall freely? Imagine standing inside a small, enclosed elevator, far from stars and planets, floating in deep space. If the elevator accelerates upward, you feel pressed to the floor, as though gravity were pulling you downward. If the elevator instead rests motionless on Earth's surface, you feel that same pressure, your feet pressing against the floor. Einstein recognized something subtle. Acceleration and gravity are locally indistinguishable. This is the equivalence principle. Within a small enough region, no experiment can tell the difference between uniform acceleration and a uniform gravitational field. If acceleration affects time, then gravity must as well. Consider a beam of light traveling upward inside an accelerating elevator. By the time the light reaches the ceiling has moved slightly upward. The light's frequency shifts slightly, its wavelength stretches. This shift is analogous to gravitational redshift. If gravity and acceleration are equivalent, then gravity must influence the frequency of light. And if gravity alters light's frequency, it must alter time itself. Clocks deeper in a gravitational field tick more slowly than clocks higher up. This is gravitational time dilation. Time passes at different rates. Depending on gravitational potential, near massive objects, time slows, not metaphorically, but physically, measurably. Atomic clocks placed at different altitudes on Earth tick at slightly different rates. Clocks higher above Earth's surface, where gravity is marginally weaker, tick slightly faster. The difference is small but detectable with precise instrumentation. Gravitational time dilation is not speculative. It is observed, confirmed repeatedly, integrated into technology. Just as motion alters duration, so does gravity. To understand why, we must let go of the classical idea of gravity as a force acting across empty space. In general relativity, gravity is not a force in the traditional sense. It is the curvature of spacetime. Mass and energy tell spacetime how to curve, and curved spacetime tells matter how to move. Imagine spacetime as a flexible fabric, not a literal surface, but a geometric continuum. A massive object, such as a star, creates curvature around it. Objects moving nearby follow paths determined by that curvature. They are not pulled by an invisible force. They follow the straightest possible paths within curved geometry. These paths are called geodesics. In flat spacetime, a geodesic is a straight line. In curved spacetime, it appears curved. The bending of light near massive bodies, observed during solar eclipses, provided early confirmation of general relativity. But beyond bending space, gravity also bends time. Near a massive object, the temporal component of spacetime is altered. Clocks closer to the mass tick more slowly. From the perspective of distant observers, this effect intensifies as mass increases. Near a neutron star, time dilation becomes pronounced. Near a black hole, it becomes extreme. Approaching the event horizon, from the viewpoint of a distant observer, a clock appears to slow dramatically, its ticking stretching further and further apart. Signals emitted from near the horizon become redshifted, their frequency decreasing, their wavelength increasing, until the signals fade. Time seems to freeze. But from the perspective of the object falling toward the black hole, its own clock ticks normally. It experiences finite proper time. The difference arises from geometry, from how spacetime curves near intense gravity. Gravitational redshift is directly measurable. Light climbing out of a gravitational well loses energy, its frequency decreases. The relationship between frequency and time means that clocks deeper in the well run slower. This was confirmed experimentally in the mid-20th century by measuring frequency shifts of gamma rays over small vertical distances. The predictions matched observation. General relativity proved accurate. The curvature of spacetime is described mathematically. By equations relating mass energy to the geometry of spacetime, the precise formulation is complex, but its meaning is clear. Mass and energy influence the metric. The way distances and durations are measured, time no longer flows independently. It responds to the distribution of mass. This reshapes our understanding profoundly. Time is not uniform across the universe. It varies depending on gravitational environment. On Earth's surface, time passes slightly slower than it would far from any mass. In orbit, time passes slightly faster than at sea level. These differences accumulate, minute by minute, year by year. In extreme gravitational fields, the differences become dramatic. Near a black hole, an observer far away may see infalling matter slow asymptotically, approaching the horizon without crossing, but for the infalling object, the crossing occurs in finite proper time. The geometry differs between perspectives, yet remains internally consistent. General relativity extends the quiet revolution. Special relativity unified space and time. General relativity makes that unity dynamic, responsive to mass and energy. Space-time is not rigid, it bends, curves, warps. The ticking of clocks becomes location-dependent. No longer determined solely by motion, but also by gravity. This has practical consequences. Global navigation systems must account not only for motion-related time dilation, but also for gravitational time dilation. Satellites experience weaker gravity than clocks on Earth. Their clocks tick slightly faster. Engineers calculate these differences precisely. Without correction, errors would accumulate rapidly. technology quietly confirms the geometry. Gravity bends time, not metaphorically, but measurably. The equivalence principle was the starting insight, a simple recognition. Acceleration and gravity share local effects. From that recognition emerged a new understanding. Space-time is not a passive stage, it participates in the dynamics of the universe. Time near mass is slower, time far from mass is faster. The flow of time depends on geometry, and geometry depends on energy and mass. This deepens the transformation. Time is no longer absolute, nor solely dependent on velocity. It is embedded within curved space-time, responsive to the distribution of matter. The universe becomes a dynamic continuum, where geometry governs duration, and duration shapes experience. The quiet revolution expands, from motion to gravity, from flat space-time to curved geometry. Time bends, not in chaos, but in order, measured, precise, consistent. The ticking of a clock is no longer universal. It is local, defined by path and position, by motion and mass, by the curvature of space-time itself. In this structure, time is not an independent river. It is a dimension woven into geometry, flexible, responsive, and quietly profound. Near an ordinary star, time slows only slightly. Near a neutron star, it slows dramatically. Near a black hole, the behavior of time becomes extreme. A black hole forms when a massive star exhausts its nuclear fuel. No longer supported by outward pressure, its core collapses under its own gravity. If the remaining mass is sufficient, nothing halts the collapse. Density increases. Curvature intensifies until an event horizon forms. The event horizon is not a physical surface. It is a boundary in space-time, a spherical region surrounding the central mass, within which the escape velocity exceeds the speed of light. No signal, no light, no information can travel outward once it crosses that boundary. To a distant observer, watching an object fall toward a black hole, the object appears to slow as it approaches the horizon. Its emitted light becomes increasingly redshifted, the frequency decreasing, the wavelength stretching. Signals arrive more slowly, more faintly, until they fade beyond detectability. From that distant perspective, the object never appears to cross the horizon. It seems to freeze at the boundary, asymptotically approaching, but never quite arriving. This effect is sometimes described as frozen time, but the phrase can mislead. Nothing physically halts. Rather, the coordinate time measured by the distant observer extends toward infinity, while the proper time experienced by the falling object remains finite. For the object itself, the crossing occurs naturally. Its own clock ticks normally. It reaches the horizon in a calculable amount of proper time. The discrepancy arises from how space-time is sliced by different observers. The distant observer defines time relative to their own position, far from the gravitational well. Where space-time curvature is weaker, in that coordinate system, the horizon represents a limit beyond which signals cannot return. Thus, signals emitted ever closer to the horizon take longer and longer to escape. From the falling object's perspective, there is no sudden halt at the horizon, no infinite waiting. Space-time geometry guides its motion inward, along a geodesic, the straightest possible path in curved space-time. The difference between coordinate time and proper time becomes essential here. Coordinate time is defined relative to a chosen reference frame, often that of a distant observer. Proper time is the time measured along the world line of an object. By a clock traveling with it, the event horizon marks a boundary in coordinate time, but not in proper time. The geometry remains consistent. Each observer describes events within their own frame, yet the underlying structure preserves coherence. Infinite redshift accompanies the approach to the horizon. As light climbs out of the deep gravitational well, it loses energy. Its frequency decreases continuously. Approaching zero, the signal becomes undetectable. To distant instruments, the falling object fades. But this fading is not destruction, it is geometric separation. Inside the horizon, all future directed paths lead inward. The curvature becomes so strong that moving outward in space would require moving backward in time, which is forbidden by causality. The event horizon thus represents a causal boundary, not a material one. It divides regions of space-time by accessibility. Black holes reveal geometry with clarity. They show that time can slow to extraordinary degrees. Depending on gravitational intensity, they demonstrate that different observers may describe the same process differently, without contradiction. For the distant observer, time near the horizon stretches. For the infalling observer, time flows normally until reaching the central singularity, where classical description breaks down. The singularity itself lies beyond current physical theory. General relativity predicts a point of infinite curvature, but quantum effects are expected to modify that prediction. What remains clear is that extreme gravity reshapes time profoundly. Black holes are not merely astronomical curiosities. They are laboratories of space-time geometry. Their existence has been confirmed through observation of gravitational waves, through imaging of event horizon silhouettes, through motion of stars orbiting unseen masses. These observations match predictions of general relativity with remarkable precision. Time dilation near black holes is not speculative. It is embedded in the equations and supported by data. The difference between coordinate and proper time illustrates a broader lesson. Time is not singular. It is contextual, dependent on path, dependent on position, dependent on curvature. In regions of weak gravity, differences are small. Near extreme mass, they become immense. The geometry remains consistent throughout. The event horizon is not a place where physics stops. It is a place where causal structure changes, where light cones tilt inward, where outward paths become impossible. This tilting of light cones visualizes how curvature shapes time and space together. As one approaches the horizon, the future light cone narrows toward the center. Inside the horizon, all future directions point inward, toward the singularity. The structure of space-time dictates inevitability, not through force, but through geometry. Black holes thus provide a clear illustration. Time does not flow independently. It bends, it stretches, it responds to mass and curvature, and observers at different positions may describe the same events differently. Yet without contradiction, the quiet revolution deepens here. Time is not universal, not constant across space, not independent of gravity. It is woven into the fabric of space-time, responsive to curvature, shaped by mass, measured along world lines. Black holes do not break time, they reveal it. In its most extreme form, precise, consistent, bound by geometry, and quietly astonishing. If different observers disagree about simultaneity, if there is no universal presence stretching across the cosmos, then a quiet possibility begins to emerge. Perhaps all events exist within a single four-dimensional structure, not unfolding one after another, but laid out together in space-time. This perspective is often called the block universe, the idea that reality is a four-dimensional continuum, where past, present, and future are not separate ontological categories, but coordinates within the same geometry. In classical intuition, the past is fixed, the present is real, and the future is open. Time appears to flow, carrying the present forward, leaving the past behind. But relativity complicates this picture, because if observers moving relative to one another disagree about which distant events are happening now, then the distinction between present and future cannot be absolute. Consider two observers moving relative to one another at constant velocity. Each defines their own plane of simultaneity. Each slices space-time differently. An event that lies in the future for one observer may lie in the present for another, provided it lies outside the light cone. If there were a single objective present moment, it would need to be the same for all observers. But relativity shows that no such universal slice exists. What remains invariant is the four-dimensional structure itself. The set of all events, connected by light cones, organized by space-time intervals. Within this framework, an object's entire history from beginning to end forms a continuous world line. Your life, in this geometric description, is not a sequence of events being created moment by moment, but a path already embedded in space-time, from birth to final event, each moment a coordinate along that line. This does not imply determinism in a simplistic sense. It does not eliminate causality. It simply reframes time as another dimension. Like space, just as all points along a spatial line exist. Even if you occupy only one at a given moment, all points along your world line exist in the geometry. The block universe does not suggest that events are unreal. It suggests that they are equally real. Across the temporal dimension, the difference between past and future becomes perspective dependent. Much as here and there are perspective dependent in space. In ordinary three-dimensional space, you occupy one location, but other locations exist simultaneously. From your perspective, some are distant, some are near, but none are more fundamentally real than others. In four-dimensional spacetime, you occupy one event along your world line, experiencing it as the present, but other events along that line exist within the same continuum. The block universe perspective aligns naturally with relativity, because relativity treats spacetime as a unified whole. Without privileging one temporal slice over another, there is no built-in flow in the equations, no advancing boundary. The mathematical structure describes the relationships between events, but does not contain a mechanism for the passage of time. This leads to philosophical reflection. If the geometry contains all events, why do we experience time as flowing? Why does the present feel unique? Why does the future seem undetermined? From the geometric standpoint, the distinction between past, present, and future arises from perspective, from the way conscious observers traverse their world lines. Each observer experiences events sequentially. Because their proper time increases along their path, they do not experience multiple coordinates at once. They experience one after another, ordered by causality. Yet the geometry itself contains the entire path. Eternalism is the philosophical term often associated with this view, the belief that all points in time are equally real, in contrast to presentism, which holds that only the present moment truly exists. Relativity challenges presentism, because the definition of present depends on frame. If the present is not universal, it cannot be the sole ontological category. The block universe does not deny change. Change is represented by differences along world lines. Different events, different states, connected by causal relations, but the structure containing them does not evolve externally. It simply is four-dimensional, complete. This view can feel unfamiliar because human experience is embedded within time. We remember the past, we anticipate the future, we act in the present. Our cognition is sequential, but the equations of relativity do not privilege that sequence. They describe spacetime as a whole. The block universe perspective emerges naturally from this description. If the present is frame-dependent, and if simultaneity varies between observers, then the division between past and future cannot be absolute. Only the causal structure defined by light cones remains invariant. Events within your past light cone have influenced you. Events within your future light cone may be influenced by you. Events outside those cones are space-like separated. Their temporal order may differ between observers, yet all reside within the same space-time manifold. The philosophical implications are subtle. They do not compel fatalism, nor eliminate agency. They simply reframe time as dimension rather than flow. Just as spatial distance does not negate movement, temporal extension does not negate experience. Within the block universe, you move along your world line, accumulating proper time, experiencing events sequentially. Even if the geometry containing those events is static, the stillness lies in the structure, not in the experience. Relativity does not explicitly demand eternalism, but it is highly compatible with it, because the theory describes spacetime without privileging a single moment. All events coexist within the mathematical manifold, connected by invariant relations. The quiet revolution deepens here. Time is not only flexible, not only curved, not only dependent on motion and gravity. It may not flow at all. It may be a dimension through which we trace paths. The sense of passage may arise from our local perspective, from the increase of proper time along our world line, but the underlying geometry remains unfolded, complete, four-dimensional. This is not a claim of certainty about ultimate reality. It is a natural interpretation of relativistic structure, a perspective emerging from invariant intervals, from light cones, from frame-dependent simultaneity. The block universe invites calm reflection, not alarm. It does not remove wonder, it reframes it, instead of a river carrying events forward. Imagine a landscape, every coordinate present within it, and you, moving steadily along a path, tracing a line through geometry, each event encountered in order, not because the universe pushes time forward, but because your world line extends through space-time. In this view, the revolution becomes complete at a conceptual level. Time is not absolute, not universal, not flowing, but geometric, structured, embedded in four-dimensional reality, quietly, precisely, and profoundly different from what intuition once assumed. If the geometry of spacetime contains all events, if past and future are coordinates within a four-dimensional structure, then another question quietly arises. Why does experience feel like a flow? Why does time seem to move? Human perception does not encounter spacetime as a static manifold. It encounters change, sequence, before and after. The sense of passage is vivid, continuous, intimate. Yet physics describes relationships between events, not an advancing present. To understand this difference, we turn inward, to the mechanisms of memory, of cognition, of entropy. The brain is a physical system, composed of matter, obeying the same laws as the rest of the universe. Its activity unfolds along a world line, increasing in proper time, each moment corresponding to a particular neural configuration. Memories are records of previous states, encoded in synaptic connections, in patterns of electrical and chemical change. When you recall yesterday, you are accessing a present neural state, containing information about an earlier event along your world line. That record exists now. The earlier event does not move into the present. Rather, the present state of your brain contains traces of earlier coordinates. There is no analogous record of future events, not because they do not exist in the geometric sense, but because information does not flow backward through light cones. Causality constrains influence. The past light cone contains events that could have affected you. The future light cone contains events you may affect. Your brain contains information from the past light cone, but not from the future. This asymmetry in information creates the feeling of temporal direction. Memory formation depends on physical processes. Neural activity requires energy. Energy transfer involves thermodynamics. Thermodynamics introduces entropy. Entropy is a measure of the number of microscopic configurations consistent with a macroscopic state. In simple terms, it reflects the degree of disorder, or more precisely, the number of possible arrangements of underlying components. The second law of thermodynamics states, in an isolated system, entropy tends to increase over time. Systems evolve from lower entropy states to higher entropy states. This statistical tendency defines an arrow of time, not imposed by fundamental equations, but emerging from boundary conditions. The early universe appears to have begun in a remarkably low entropy state, highly ordered, uniform. As the universe expands, entropy increases, stars form, burn fuel, release energy, energy flows, structures form and dissolve. The increase of entropy gives physical processes a direction. Eggs break, but do not spontaneously reassemble. Heat flows from hot to cold, but not the reverse. Memory formation relies on entropy increase. To encode information, the brain must consume energy, increase entropy in its surroundings. The creation of a memory is not thermodynamically neutral. It is embedded within irreversible processes. Thus, the brain naturally records events in one temporal direction. Toward increasing entropy, the psychological arrow of time aligns with the thermodynamic arrow. We remember the past because entropy was lower, and records could be formed. We do not remember the future because entropy has not yet increased in those ways. The subjective experience of flow arises from continuous change in neural states, each new state encoding information about previous ones, but not vice versa. Cognitive sequencing reinforces this. The brain processes stimuli in ordered chains. Perception unfolds in milliseconds. Signals travel along neurons, activating networks, producing coherent awareness. This awareness is temporally extended, but only locally. We experience a narrow window, often called the specious present, a brief duration integrating recent sensory input. Within that window, events feel simultaneous. Outside it, they are ordered, before, after. The brain constructs continuity by linking these windows, creating the impression of a flowing present. But from a physical perspective, each neural configuration exists at a specific spacetime coordinate. Each moment of awareness corresponds to one event along the world line of the brain. The next moment corresponds to the next coordinate. Connected by causal processes, the feeling of motion through time arises because successive brain states differ, each containing records of earlier states. Entropy underlies this asymmetry. Because entropy increases, the universe provides a direction in which records accumulate. This accumulation defines the psychological arrow. Physics, at its most fundamental level, often exhibits time symmetry. Equations remain valid if time is reversed, but entropy introduces statistical asymmetry. Low entropy boundary conditions at the beginning of the universe allow complexity and memory to emerge in one temporal direction. Thus, experience aligns with thermodynamics. not with a fundamental flowing time. The block universe perspective remains compatible with this. All events exist within spacetime, but the distribution of entropy differs across that manifold. Regions corresponding to earlier cosmic times had lower entropy. Later regions have higher entropy. Observers embedded within that structure experience direction because of that gradient, not because spacetime itself advances. Cognitive systems like the human brain operate within that gradient, forming memories in one direction, anticipating possibilities in the other. The future feels open because information about it is incomplete, not because it does not exist geometrically. Our ignorance of future coordinates along our world line is not evidence of non-existence. It reflects causal structure and entropy. The psychological flow of time thus emerges from physical processes: memory formation, energy consumption, entropy increase, sequential neural activation. These mechanisms produce the vivid sense of passage, even if spacetime itself is static in the geometric sense. Experience does not contradict physics. It arises within it. The revolution is subtle here. Time may not flow at the fundamental level, yet flow appears within complex systems, because entropy increases, because information accumulates, because brains encode sequences. The quiet distinction between physics and perception becomes clear. Physics describes relationships between events. Perception describes the ordered traversal of events along a world line. The sense of now, the sense of before and after, emerges from the structure of memory and entropy, not from an advancing cosmic present. In this understanding, there is no conflict between geometry and experience, only layers of description. At one level, spacetime is a four-dimensional manifold, complete, structured. At another, conscious systems trace paths within it, forming records, experiencing change, feeling time's passage. Both perspectives coexist, one analytical, one experiential, bound together by thermodynamics, by entropy, by neural processes. The flow you feel is real, but it is a property of physical systems within spacetime, not of spacetime itself. Time may not move, yet we move through it, along our world lines. Gathering memories, increasing entropy, experiencing sequence, within a geometry that remains silent, complete, and quietly profound. The feeling of temporal direction, the sense that time moves from past to future, finds its deepest physical expression in thermodynamics. In particular, in the second law. The second law of thermodynamics states, in an isolated system, entropy does not decrease. It either remains constant or increases. To understand this, we begin with statistical mechanics, the branch of physics that connects microscopic motion with macroscopic properties. At the microscopic level, matter consists of particles, atoms, molecules, each moving, colliding, interacting according to fundamental laws. These microscopic laws, whether Newtonian in classical mechanics or quantum mechanical at small scales, are largely time-symmetric. If one reverses the direction of time in their equations, they remain valid. A movie of particle motion played backward still satisfies the fundamental laws, yet at the macroscopic level, irreversibility appears everywhere. Ice melts in warm air, but water does not spontaneously gather heat from its surroundings to refreeze. Cream mixes into coffee, but does not unmix itself. These processes have direction. The concept of entropy resolves this tension. Entropy measures the number of microscopic configurations that correspond to a given macroscopic state. A highly ordered system has relatively few microscopic arrangements. A disordered system has vastly more. For example, consider a box divided into two halves, with gas initially confined to one side. When the barrier is removed, the gas spreads out, filling the entire box. The spread-out state corresponds to far more microscopic arrangements than the confined state. Statistically, the system is overwhelmingly more likely to be found in the higher entropy configuration, not because the laws forbid reversal, but because reversal is extraordinarily improbable. The second law is statistical, not absolute. Given sufficient time, rare fluctuations could reduce entropy locally. But in practice, for systems of astronomical numbers of particles, entropy increase dominates. This statistical tendency gives macroscopic processes their direction. The arrow of time in thermodynamics points toward increasing entropy. The profound question arises, why was entropy low in the past? Particularly at the beginning of the universe, observations suggest that the early universe was remarkably uniform, nearly homogeneous, with small fluctuations in density. Uniformity may seem disordered at first glance, but gravitational systems behave differently. For systems dominated by gravity, clump structures correspond to higher entropy. Stars, galaxies, black holes represent higher gravitational entropy. The early universe's smoothness therefore represented a low entropy state. As the universe expanded, structure formed, matter clumped, entropy increased, stars ignited, nuclear reactions released energy, driving further entropy production. The thermodynamic arrow of time thus aligns with cosmic history, from a low entropy beginning toward increasing complexity and disorder. Fundamental equations of motion remain time-symmetric. But the boundary condition of low initial entropy introduces asymmetry. The arrow of time emerges from initial conditions, not from the basic laws themselves. This distinction is essential. At the microscopic level, time does not inherently prefer a direction. At the macroscopic level, entropy defines one. Why does entropy increase? Because systems evolve toward more probable configurations. Probability governs macroscopic behavior. Given many particles, the overwhelmingly likely evolution is toward higher entropy. This probabilistic reasoning underlies the arrow of time. Disorder grows, not because order is forbidden, but because disorder corresponds to vastly more microscopic states. The connection between entropy and information deepens the story. Entropy can be interpreted as missing information about microscopic detail. As entropy increases, information about precise initial conditions becomes inaccessible. When cream mixes into coffee, the detailed arrangement of molecules becomes effectively lost. The macroscopic state appears uniform, but microscopic correlations are dispersed, irretrievable in practice. This irretrievability creates irreversibility. The second law therefore underpins the psychological arrow of time. Memory formation depends on entropy increase. As discussed earlier, records form because energy flows, because entropy increases in the environment. The arrow of time experienced by conscious beings is rooted in thermodynamics, yet the fundamental equations remain symmetric. This duality is subtle. The universe's large-scale history provides direction, the microscopic laws do not. Low entropy in the early universe is one of the deepest puzzles in physics. Why did the universe begin in such an ordered state? Why was gravitational entropy low? Various hypotheses exist. Some propose that inflationary expansion smoothed spacetime. Others suggest deeper cosmological principles. But the fact remains, the arrow of time points away from that low entropy boundary. The direction we call future is the direction of increasing entropy. This explains why we remember the past. The past corresponds to lower entropy states, which leave records in higher entropy states. The future corresponds to states of even higher entropy, which have not yet left records. Entropy therefore generates asymmetry. Even though the underlying equations are time-symmetric, the quiet revolution deepens again. Time's direction is not written into the laws of motion. It emerges from statistical conditions, from probability, from initial order. The arrow of time is contingent, not fundamental. If the universe had begun in a high entropy state, no macroscopic arrow would exist, no complex structures would form, no records would accumulate, no observers would arise to reflect on time. The existence of complexity depends on entropy gradients. Energy differences drive processes. Stars radiate because their cores are hotter than surrounding space. Living systems exist because energy flows from low entropy sources to high entropy sinks. All of this relies on the second law. Entropy increases, creating direction, within a spacetime that may itself be static geometrically. The thermodynamic arrow does not contradict the block universe. It defines a gradient within it, a direction along world lines, corresponding to increasing entropy. From low entropy past coordinates to higher entropy future coordinates. The distinction between symmetry in equations and asymmetry in boundary conditions is central to understanding time. Fundamental dynamics do not force time to move forward. Statistical structure makes forward overwhelmingly likely. This statistical inevitability shapes experience, shapes memory, shapes causality. The second law stands quietly beneath everyday life, guiding processes, ensuring irreversibility, embedding direction in macroscopic reality. Time's arrow emerges not from deep metaphysical flow, but from probability, from the counting of microscopic states, from the remarkable low entropy of the early universe. The revolution becomes clearer. Time's direction is emergent, not imposed by fundamental equations, arising from statistical mechanics, from thermodynamic gradients, from the quiet arithmetic of probability. In this understanding, time's arrow is real, yet not fundamental, rooted in entropy, shaped by boundary conditions, flowing not because space-time pushes forward, but because disorder grows, because probability favors certain directions, because the early universe began in extraordinary order, and from that order, entropy increases, defining the direction we call future, steady, statistical, unfolding along world lines within a geometry that remains silent, complete, and profoundly structured. The second law gives direction. Entropy increases, records accumulate, irreversibility emerges. Yet beneath this macroscopic asymmetry, the fundamental equations remain largely indifferent to time's direction. This is the next layer of the quiet revolution. At the microscopic scale, the laws of physics are nearly time-reversible. In classical mechanics, if you reverse the velocities of every particle and allow the system to evolve, the equations remain satisfied. The reversed motion is equally valid. In quantum mechanics, the situation is similar. The Schrödinger equation, which governs the evolution of the quantum wave function, is symmetric under time reversal if time is replaced with its negative, and certain complex quantities are appropriately conjugated. The structure of the equation remains intact. There is no built-in arrow. The fundamental interactions, electromagnetic, weak nuclear, strong nuclear, and gravitational, are described by equations that, to a very high degree of precision, respect time symmetry. More precisely, they respect a deeper symmetry known as CPT symmetry. CPT stands for charge conjugation, parity transformation. And time reversal. Charge conjugation replaces particles with their antiparticles. Parity transformation inverts spatial coordinates, turning left into right. Time reversal replaces time with its negative. The combined operation of CPT is believed to be an exact symmetry of nature. According to current quantum field theory, this means that if one applies all three transformations together, the laws remain invariant. Even if time reversal alone is not perfectly symmetric in all cases, the combined symmetry ensures deep consistency. There are subtle violations of certain symmetries. For example, in weak nuclear interactions, there exist small violations of CP symmetry, which implies small violations of time reversal symmetry. But these effects are minute and do not dominate macroscopic behavior. For most practical purposes, the fundamental equations do not distinguish past from future. This creates a striking contrast. At the microscopic level, reversibility; at the macroscopic level, irreversibility. The distinction lies in statistics and boundary conditions, not in dynamical laws themselves. The Schrödinger equation governs how quantum states evolve in time. It is linear, deterministic in its evolution of the wave function. Given an initial wave function, the future evolution is uniquely determined, but the equation does not require that time move forward. It functions equally well in reverse. The apparent asymmetry in quantum mechanics often enters through measurement, when a quantum system interacts with a measuring apparatus and the outcome appears definite. Some interpretations describe this as wave function collapse, an irreversible process. But whether collapse represents a fundamental physical asymmetry or an effective description arising from decoherence remains debated. In decoherence theory, a quantum system interacting with its environment becomes entangled with many degrees of freedom. Interference between alternatives becomes effectively inaccessible. The appearance of collapse arises from environmental entanglement, which itself is governed by time-symmetric equations. Again, the asymmetry appears in practice, but not in fundamental structure. Where then does asymmetry truly emerge? From entropy, from the low entropy condition of the early universe. The microscopic laws permit reversal, but the universe's boundary conditions bias evolution toward increasing entropy. The thermodynamic arrow overlays time-symmetric laws, creating effective irreversibility. This layering of symmetry and asymmetry is subtle and profoundly important. It means that time's direction is not imposed at the deepest level. It emerges from initial conditions and statistical structure. If one could prepare a system in a highly special microscopic configuration, it could evolve toward lower entropy, but such configurations are extraordinarily improbable. The universe's initial state appears to have been such a special configuration, low entropy, highly ordered. From that condition, entropy increases. Defining the arrow, the microscopic equations remain neutral. They allow both directions, but probability favors one. This realization reshapes intuition again. Time's arrow is emergent, not fundamental. Reversibility at the smallest scales, irreversibility at larger scales, connected through statistics, connected through entropy, connected through boundary conditions. Even gravity, in general relativity, is described by equations symmetric in time. Space-time curvature evolves according to differential equations, which do not inherently select past or future. Black holes form when matter collapses. But mathematically, one can describe time-reverse solutions, white holes, objects that emit matter, though such configurations are not observed in nature because entropy conditions make them improbable. The asymmetry we observe is not enforced by local equations, but by the global history of the universe. This distinction is difficult because human intuition often assumes that direction must be fundamental, yet physics suggests otherwise. At its deepest level, time may be symmetrical, a dimension like space with direction emerging from statistical imbalance. This view reinforces the geometric picture. If space-time is a four-dimensional manifold, and if its fundamental laws are time-symmetric, then the sense of forward motion is not embedded in geometry. It arises from entropy gradients within that geometry. Observers exist because entropy increases. Complex systems form because energy flows from low to high entropy. Memory exists because entropy production leaves records. The arrow of time is tied to complexity, not to the equations themselves. This understanding deepens the quiet revolution. Time does not push the universe forward. The universe evolves according to symmetric laws, from special initial conditions, producing asymmetric experience. The apparent flow is layered. At one level, symmetric equations; at another, statistical bias; at another, cognitive experience, each layer consistent, each layer real within its domain, but none requiring a universal advancing present. The paradox dissolves gently. Time's direction is not a fundamental force. It is an emergent feature of entropy. Within a space-time whose equations are nearly indifferent to temporal orientation, the revolution remains quiet. No explosion of certainty, no dramatic rupture, only a gradual reshaping of understanding, from absolute flow to geometric structure, from intrinsic direction to emergent asymmetry, from intuition to analysis. Time symmetry at the fundamental level and time asymmetry at the macroscopic level coexist. Connected through probability, through entropy, through the remarkable low-entropy origin of the cosmos. The equations do not demand a direction. The universe's history supplies one, steady, statistical, layered, and quietly profound. At very small scales, the universe is not described by definite trajectories, not by precise positions and velocities evolving continuously. Instead, it is described by possibilities. A quantum state does not specify what is. It specifies what may be observed. The central object is the wave function, a mathematical structure assigning amplitudes to configurations. From these amplitudes, probabilities emerge when measurement occurs. But between measurements, the wave function evolves smoothly. According to the Schrödinger equation, this evolution is continuous, deterministic, and time-symmetric. If the direction of time is reversed, the equation still holds. No preferred orientation is embedded in its form, yet human experience contains definite outcomes. A particle is detected here. A detector clicks once, a position becomes known. This contrast introduces the measurement problem. How does a spread of possibilities become a single result? Some interpretations describe a collapse, an abrupt change from many possibilities to one. If collapse were fundamental, it would introduce an intrinsic direction to time. Because collapse appears irreversible, once an outcome is recorded, it does not spontaneously unrecord. However, there exists another perspective, in which no collapse occurs at all. Instead, the quantum system becomes entangled with its environment. A measuring device interacts with a particle. The device itself is composed of atoms. Those atoms interact with surrounding air. Photons scatter. Information spreads outward. The combined system evolves into a superposition of correlated states, each branch internally consistent, each containing a definite outcome. The appearance of a single result emerges, because interference between branches becomes inaccessible. This process is called decoherence. Decoherence does not break time symmetry. It follows from ordinary quantum evolution. but it produces practical irreversibility, because reconstructing the original coherent state would require reversing interactions of astronomically many particles. Not impossible in principle, but overwhelmingly improbable. Thus the arrow again appears, not from fundamental law, but from complexity. Quantum theory therefore mirrors thermodynamics. Symmetric equations, asymmetric experience, time's direction emerging statistically. Entanglement introduces another subtle feature. Correlations exist across distance. Two particles may share a joint quantum state. Even when separated by large spatial intervals, a measurement on one predicts the outcome of the other. Yet no signal travels faster than light. The correlations are built into the shared state, not transmitted through space. These correlations also do not require a preferred time ordering. Different observers may disagree about which measurement happened first, but predictions remain consistent. Quantum theory respects relativistic causality. While refusing classical intuitions about sequence, events are not always strictly ordered globally, only locally within light cones. This reinforces a growing pattern. Temporal order is less absolute than intuition suggests, even at the quantum level. Another question arises. Does quantum mechanics itself require time as a fundamental parameter? In the Schrödinger equation, time appears as an external variable, a background parameter. Yet when gravity enters the picture, the situation changes. General relativity does not treat time as external. It treats time as geometry. If one attempts to quantize gravity, combining quantum theory with curved spacetime, the role of time becomes uncertain. In certain formulations, the fundamental equation describing the universe contains no time variable at all. The wave function of the universe simply exists, describing correlations among configurations without evolving through an external clock. Dynamics becomes relational. One part of the system changes relative to another, but no universal parameter ticks. Time emerges from internal correlations. Consider a simple analogy. A clock is a physical system. Its hands move relative to its face. But the motion itself is defined only relative to other processes. If every physical change slowed proportionally, no internal observer could detect a difference. In quantum gravity proposals, the universe may function similarly. There is no external time, only relationships among variables, a configuration where one subsystem acts as a reference, allowing others to be described as evolving relative to it. This is sometimes called relational time not as a universal flow, but as ordering among states. The apparent passage arises from correlations between subsystems. Memory states correlated with prior configurations. Prediction states correlated with possible later configurations. The universe becomes a network of relations, rather than a sequence of instants. Another subtlety appears in quantum cosmology. The total energy of a closed universe may be zero, positive contributions balanced by negative gravitational energy. In such a system, the traditional time parameter associated with energy evolution may disappear from the fundamental equation. The universe's quantum state becomes static, yet observers inside still experience change, because subsystems serve as clocks relative to others. Thus, experience of time does not require a fundamental time variable. It requires correlation structure. Memory records earlier correlations. Prediction anticipates future correlations. The mind interprets this ordered structure as flow. Quantum theory therefore suggests time may not be primary, it may be emergent from entanglement patterns, from information relationships, from statistical structure. Measurement does not introduce time, it reveals correlations within a timeless description. Different interpretations emphasize different aspects. Some describe branching histories, some describe hidden variables guiding outcomes, some describe consistent histories without collapse. Each attempts to reconcile definite experience with symmetric laws. None requires a universal moving present. Across interpretations, a shared lesson remains. Temporal order is contextual, defined within interactions, not imposed globally. Causality remains intact locally. Signals cannot outrun light, but beyond causal contact, global ordering loses meaning. Quantum theory therefore complements relativity. Relativity removes universal simultaneity. Quantum theory removes definite trajectories. Together they soften the concept of a universal timeline. Events form a network, not a single advancing edge. The observer participates in this network. By becoming correlated with particular states, memory is a physical record, stored in neural configurations. Those configurations correlate with past events, not future ones. Because entropy grows, and decoherence spreads information outward, thus subjective time arises. From physical correlations increasing in complexity, not from a fundamental ticking parameter. At deeper levels, the universe may simply be a structured set of relations containing ordered records within which awareness traces a path. Quantum mechanics does not fully solve the mystery, but it reshapes the question. Instead of asking, how does time flow, one asks, how do correlations give rise to sequence? The answer appears layered: symmetric equations, statistical asymmetry, cognitive interpretation. The quiet revolution continues. Time becomes less a moving river and more a pattern, less a process and more a relation, less an external parameter and more an emergent description. Within the deep structure of reality, change exists, but perhaps not passage. Order exists, but perhaps not motion of the present. Experience remains real, yet its foundation becomes geometric, informational, relational, and gently independent of any universal ticking clock. At the largest scales, time stretches beyond laboratories, beyond clocks on satellites, beyond particle detectors, into the structure of the cosmos itself. Cosmology begins with a simple observation. Distant galaxies are receding. The universe is expanding. This expansion is not motion through space, it is the growth of space itself. Distances between galaxies increase because the metric that measures separation evolves. This expansion implies a denser past. If one traces the equations backward, matter becomes compressed, temperatures rise, radiation intensifies. Approximately 13.8 billion years ago, the observable universe was in an extremely hot, extremely dense state. This moment is called the Big Bang, not an explosion into pre-existing space, but the beginning of expansion within spacetime itself. The equations of general relativity describe this expansion. When combined with a homogeneous and isotropic assumption, they yield solutions in which the scale factor changes with time. The scale factor describes how cosmic distances grow. As it increases, galaxies drift apart. As it decreases towards zero, density and temperature rise. In these models, time is a coordinate woven into space-time geometry. Proper time along world lines of comoving observers measures the age of the universe. Observers at rest, relative to cosmic expansion, share a common cosmic time parameter. This cosmic time is not universal in the Newtonian sense, but it provides a natural slicing of space-time. Based on large-scale symmetry, evidence for a hot early universe is preserved in radiation. The cosmic microwave background, a faint glow filling all directions. Discovered in the 20th century, this radiation corresponds to light released approximately 380,000 years after expansion began, when the universe cooled enough for electrons and protons to combine, forming neutral hydrogen. Before that moment, photons scattered constantly from charged particles. After recombination, light traveled freely, stretching in wavelength as space expanded. Today it appears as microwave radiation, extremely uniform with tiny fluctuations. Those fluctuations seeded galaxies, clusters, large-scale structure. The cosmic microwave background acts as a record, a snapshot of early conditions. It confirms that cosmic time has measurable structure. Not merely philosophical speculation, yet questions remain. Did time itself begin at the Big Bang, or did something precede it? General relativity predicts a singularity, a boundary where curvature diverges, where density becomes infinite, where classical equations break down. However, many physicists suspect that singularities signal incomplete theory. Quantum gravity likely modifies behavior at extreme density, replacing singularity with new structure. Some models propose a bounce, a prior contracting phase transitioning to expansion. Others propose eternal inflation, where expansion continues in multiple regions, generating distinct cosmic domains. In these frameworks, the Big Bang is not the absolute beginning of time, but a transition within a broader process. Even so, observable cosmic time appears finite. Tracing back to early high-energy conditions, cosmology also introduces horizons. Because light travels at finite speed, we observe only a finite region, the observable universe. Beyond that horizon, regions may exist beyond causal contact. Time within those regions unfolds according to their own histories, but signals cannot reach us. Thus, cosmic time is locally defined. Within the patch accessible to observation, another concept emerges: inflation, a hypothesized rapid exponential expansion, occurring fractions of a second after the beginning. Inflation smooths irregularities, explains observed flatness, and accounts for near uniformity of the cosmic microwave background. During inflation, the scale factor increases dramatically, stretching quantum fluctuations to cosmic scales. These fluctuations later become density variations. Time during inflation is described within relativistic equations, yet its physical meaning remains tied to expansion rate. In quantum cosmology, time may not exist at the most fundamental description. The wave function of the universe may encode all possible geometries simultaneously. Without evolving in external time, what appears as cosmic history may correspond to correlations among configurations. Some configurations resemble early dense states. Others resemble later dilute states. Observers embedded within particular configurations perceive ordered sequence. Because entropy differs among them, low entropy in early conditions, higher entropy later. This gradient produces thermodynamic arrow, which aligns with cosmic expansion. Entropy increases as structure forms. Stars ignite, galaxies evolve, black holes grow, energy disperses. The early universe possessed remarkably low entropy, despite extreme density. Gravitational degrees of freedom were highly ordered. As expansion continued, gravity amplified small inhomogeneities, generating complexity. This increase in gravitational entropy contributes to arrow of time. Thus, cosmological initial conditions underpin thermodynamic asymmetry. Time direction in experience traces back to cosmic origin, not from local equations, but from global boundary conditions. Cosmic time also shapes stellar evolution. Stars burn nuclear fuel over millions or billions of years. Their lifetimes depend on mass. Massive stars evolve rapidly. Less massive stars persist far longer. This temporal hierarchy structures cosmic history. Elements heavier than hydrogen and helium form in stellar cores and in explosive deaths of massive stars. These elements become planets. Biology, observers, thus conscious reflection on time, is a late development in cosmic chronology. Emerging billions of years after expansion began, the universe itself ages. But aging is relative to chosen clocks. Observers measure age using atomic transitions, comparing frequencies of radiation. These clocks are influenced by gravitational potential and relative motion. Yet cosmological time slicing provides a convenient framework. Because of large-scale uniformity, if expansion continues indefinitely, the future universe may approach thermal equilibrium. Stars exhaust fuel, galaxies dim, black holes evaporate over enormous durations. On timescales vastly exceeding current age, the universe may approach maximum entropy, sometimes called heat death. In that scenario, temporal change becomes subtle, gradients flatten, energy differences diminish. Yet even then, quantum fluctuations persist, geometry continues, time as relational ordering remains, though dramatic evolution subsides. Alternatively, if dark energy evolves differently, expansion might accelerate forever or reverse in distant epochs. Cosmological models explore many possibilities, each defined by equations connecting energy density, curvature, and expansion rate, but all remain rooted in geometry. Time is embedded within spacetime structure, not external to it. Thus, cosmology reinforces earlier lessons. Time is not a flowing substance. It is a dimension intertwined with space, defined by metric relations, measured by world lines of observers, conditioned by entropy, shaped by gravity. The beginning of time debate remains open. Some argue that asking what came before the Big Bang is like asking what lies north of the North Pole. If time began with expansion before has no meaning. Others suggest that deeper theory reveals prior structure, where time extends beyond observable horizon. In either case, the intuitive notion of universal flowing now finds no support at cosmic scale. Instead, there is a manifold, a four-dimensional structure, within which cosmic evolution is encoded. Observers trace world lines through it, measuring intervals along their paths. Cosmic microwave background, galaxy redshift surveys, supernova observations, all align with relativistic description. Time in cosmology is measurable, predictable, yet not absolute. It depends on geometry and matter content. The quiet revolution thus extends outward, from trains and clocks to galaxies and background radiation, from laboratory thought experiments to the entire observable universe. Time does not flow across cosmic emptiness. It is structured within it, encoded in expansion, bound to entropy, emergent from geometry, and perhaps at the deepest level, not fundamental at all, but arising from relations among states, across the vast, ever-expanding silent architecture of spacetime. In the deepest attempts to understand gravity and quantum mechanics together, time begins to loosen further. General relativity describes spacetime as dynamic geometry. Quantum mechanics describes physical systems using wave functions that evolve with respect to time. But when one attempts to quantize gravity itself, a curious feature appears. In certain formulations of quantum gravity, the fundamental equation does not contain time at all. One of the most well-known examples is the Wheeler-DeWitt equation. This equation is written in a form that resembles the Schrödinger equation, but without the time derivative term. It takes the form: the Hamiltonian constraint acting on the wave function of the universe equals 0. In words, the total energy of the universe constrains its quantum state, and that state does not evolve in external time. The wave function is static. A frozen description of all possible geometries and matter configurations. This absence of time in the equation has been called the problem of time, because our experience is filled with temporal succession. Yet the fundamental equation seems timeless. How can change arise if the underlying description does not evolve? One approach suggests that time is emergent, not fundamental. In this view, what we call time arises from correlations between parts of a larger system. If one subsystem behaves predictably, its configuration can serve as a clock. Other subsystems can be described relative to it. Time becomes relational, not absolute. Imagine a universe described by a single quantum state. Within that state, some variables change with respect to others. An observer identifies one degree of freedom as a clock variable, then describes how other variables correlate with it. In this framework, there is no external time parameter, only relationships among configurations. Time is the ordering of these correlations. Another proposal suggests that entropy itself defines time. As entanglement between subsystems increases, observers perceive progression. The arrow of time aligns with growth of entanglement entropy. This connects quantum information theory with temporal experience. The notion of emergent time also appears in approaches such as loop quantum gravity, where spacetime geometry is quantized into discrete structures. Spin networks represent quantum states of geometry. Their evolution may not require background time. Instead, transitions between configurations define effective temporal ordering. Similarly, in holographic theories, such as those inspired by the anti-de Sitter correspondence, time in a gravitational bulk region may correspond to properties of a lower dimensional boundary theory. Temporal behavior becomes dual to quantum dynamics on that boundary. In these pictures, time is not an independent backdrop. It arises from deeper structure. Some physicists explore the idea that the universe as a whole is described by a single timeless wave function. Within that wave function, certain regions appear classical. Through decoherence, observers embedded within those classical branches perceive evolution. Because memory records are correlated with specific configurations, sequence emerges from consistency of records. You remember earlier states, because the present configuration encodes traces of them, but the global description remains static. This perspective resembles the block universe, yet goes further, because even spacetime geometry may not be fundamental. Instead, spacetime could emerge from entanglement patterns. Recent research in quantum gravity suggests that geometric distance may correspond to strength of entanglement between subsystems. Highly entangled systems appear close in emergent space. Weakly entangled systems appear distant. If spatial relations arise from entanglement, temporal relations may also emerge from information flow. Another approach, known as causal set theory, attempts to build spacetime from discrete events ordered by causality. In this framework, fundamental structure is a partially ordered set. Events relate through cause and effect. The number of elements between two events approximates spacetime volume. Time becomes the ordering relation itself, rather than a continuous dimension. Other models consider thermodynamic time as fundamental, proposing that time's arrow defines spacetime orientation. Instead of being derived from geometry, yet none of these proposals are experimentally confirmed. They remain theoretical explorations. Careful attempts to reconcile quantum mechanics and gravity The Wheeler-DeWitt equation remains central in these discussions. Its form implies that the universe satisfies a constraint. Rather than an evolution equation, observers who isolate subsystems may recover effective Schrödinger evolution when treating other degrees of freedom as clocks. Thus, time appears in approximation, not in the exact equation. This suggests that time as we know it may be an emergent parameter, valid within semi-classical limits, but absent in the full quantum description. Such ideas challenge intuition deeply. If the universe is fundamentally timeless, then past and future distinctions arise from perspective within configuration space. Memory records create apparent flow, but the global state remains, complete, unchanging. Some philosophers interpret this as ultimate block reality. Others argue that emergence does not eliminate change, but relocates it to relational structure. Time becomes a useful coordinate, defined by observers, within certain regimes. The idea of relational time can be traced back to Leibniz, who argued that time is not a thing in itself, but a measure of change among objects. Modern physics echoes this intuition. Without invoking metaphysical speculation, the mathematics guides the interpretation. When background independence is enforced, external time disappears. In general relativity, there is no preferred global time coordinate. Different foliations describe spacetime equally well. In quantum gravity, even those foliations may lose meaning, leaving only relations among quantum states. Yet in everyday life, time feels persistent. We plan, we anticipate, we age. These experiences are real within effective descriptions. Emergence does not imply illusion. Temperature emerges from molecular motion, yet remains physically meaningful. Likewise, time may emerge from deeper relations, while remaining operationally precise within accessible scales. Thus, timeless theories do not deny temporal experience. They seek to understand its origin. Why does the universe permit observers who perceive sequence? Perhaps because entropy gradients exist, because memory storage is possible, because quantum decoherence stabilizes classical histories. These conditions allow effective time to arise, even if the fundamental equation remains silent about flow. In summary, timeless approaches suggest that the deepest description of reality may not contain a ticking parameter. Instead, all configurations coexist within a quantum state. Correlations among them generate apparent succession. Observers embedded within specific correlations interpret those relations as past, present, future. Time becomes an ordering principle, not a flowing substance, a structural feature emerging from information and geometry, rather than a fundamental ingredient. The quiet revolution thus continues. What began as correction to simultaneity has become a reconsideration of existence itself. Time may not be fundamental, yet it remains profoundly meaningful. Because within emergent structures, world lines still trace paths, stars still evolve, and conscious beings still ask, how long and why, and whether time at the deepest level is simply a relation among states within an unchanging whole. Time did not shatter in a single dramatic moment. It was not overturned with noise, it was gently reinterpreted. What once appeared as a universal river became geometry. What once seemed absolute became relational. The transformation began with a simple insistence that the laws of physics must look the same in all inertial frames, and that light travels at a constant speed, independent of the motion of its source. From these two postulates, the structure of time quietly shifted, simultaneity dissolved. Two observers moving relative to one another no longer agree on which distant events occur at the same moment. The concept of a universal now faded, not through philosophy, but through calculation. The Lorentz transformations replaced Galilean intuition. Space and time coordinates mixed together. Depending on motion, time dilation emerged. A moving clock ticks more slowly, not because it is malfunctioning, but because space-time geometry demands it. Proper time became the invariant measure along a world line. Different observers slice space-time differently, but the space-time interval remains unchanged. Length contraction followed naturally. Objects in motion appear shorter along the direction of travel, not because they are compressed by force, but because spatial and temporal components are inseparable. Hermann Minkowski formalized this insight, declaring that space and time form a single four-dimensional continuum. Space-time, events are points within this manifold. World lines trace histories. Motion becomes a change in orientation within space-time. Velocity corresponds to rotation between temporal and spatial components. Geometry replaces absolute background, then gravity itself transformed. The equivalence principle revealed that inertial and gravitational mass are indistinguishable. An accelerating frame mimics gravitational influence. From this insight, general relativity emerged. Mass and energy curve spacetime, and free-falling objects follow geodesics within that curvature. Clocks tick at different rates depending on gravitational potential. Near massive bodies, time slows. Gravitational redshift confirms this experimentally. Atomic clocks placed at different altitudes tick at measurably different rates. Global positioning satellites correct for both special and general relativistic effects. Without those corrections, navigation systems would drift by kilometers each day. Black holes extend this curvature to extremes. At the event horizon, an external observer sees infalling objects appear to freeze. Light from them redshifts toward invisibility. Yet for the falling observer, proper time continues smoothly. There is no abrupt halt at the horizon, only inevitable approach toward regions of stronger curvature. These phenomena do not introduce contradiction. They reveal coordinate dependence. Different observers describe events using different parameterizations, but spacetime itself remains consistent. Relativity therefore suggests a block universe interpretation. All events exist within the four-dimensional manifold. Past and future are coordinates, not destinations yet to be created. Your birth, your present awareness, your distant future, all occupy positions along your world line. This does not negate experience, it reframes it. The flow of time may arise from entropy, from thermodynamic asymmetry, from memory encoding low-entropy past states. The fundamental equations of physics are largely time-symmetric, yet entropy increases statistically, producing the arrow of time. Quantum mechanics complicates this further. The Schrödinger equation evolves symmetrically in time, yet measurement introduces apparent irreversibility. Interpretations differ, but the mathematics remains precise. In quantum gravity, the Wheeler-DeWitt equation omits external time entirely, suggesting that at the deepest level, the universe may be described by a timeless state. Emergent time arises from correlations among subsystems. Observers embedded within those correlations perceive succession. Thus, Einstein's revolution extends beyond special relativity. It reshapes ontology. Reality is not a stage upon which events unfold in a universal present. Reality is a structured space-time manifold, within which relations define measurement. Observer dependence is not subjectivity. It is invariance under transformation. All observers agree on the space-time interval. Even when they disagree on simultaneity, this invariance anchors physical law. Beneath motion, there is stillness. Beneath ticking clocks, there is geometry. The transformation of time did not remove meaning, it deepened it. Because now, every moment is embedded in a consistent structure. Every event has coordinates. Every world line traces an entire history. Einstein did not seek to destroy intuition, he sought coherence, and coherence required relinquishing absolute time. In its place, we gained a unified spacetime, curved by mass, measured by light, and structured by invariant intervals. The humility of this revolution lies in its restraint. It did not proclaim time an illusion. It revealed its dependence on motion and gravity. It showed that what feels universal may be local, what feels flowing may be geometric. This reinterpretation does not diminish wonder, it refines it, because the cosmos now appears as a consistent fabric, not chaotic flux. World lines weave through curvature, light cones structure causality, entropy gradients guide perception. Quantum states encode correlations, and within this architecture, conscious awareness unfolds along specific paths. Time remains meaningful operationally. We measure intervals, we schedule events, we predict outcomes, yet we understand that these measurements depend on frame and curvature. The present is not absolute, it is defined by local conditions. The revolution remains quiet, because nothing in daily life visibly fractures. Clocks still tick, aging continues. Stars rise and set. But beneath those familiar patterns, the foundation is transformed. Time is not a universal river, it is a coordinate woven into space-time, dependent on motion, shaped by gravity, emergent from correlation. Einstein's insight reminds us that certainty can be provisional, that intuition may require revision, that simplicity can conceal depth. The laws governing the universe do not bend to expectation. They reveal themselves through careful reasoning, and sometimes through a willingness to question what appears obvious. Time was once assumed to be the same everywhere. Now we understand that it is local, relative, integrated with space, curved by mass, and possibly emergent from deeper quantum structure. This is not instability, it is structure revealed, a geometry where events coexist, where causality is preserved, where invariants anchor transformation, and where awareness traces a path. Within a manifold that does not rush, it simply is. The quiet revolution does not end in disruption. It ends in clarity. Time did not disappear, it transformed. And in that transformation, the universe became more coherent, more unified, more profoundly ordered. We remain travelers along world lines, but now we understand that the road is not laid out by a flowing present. It is embedded in geometry, silent, consistent, and vast, enough to hold every moment without hurry, without loss, within the calm architecture of space-time itself. You are not moving through time in the way you once imagined. You are tracing a world line within a four-dimensional geometry. Every breath you take, every memory you hold, every future possibility you anticipate is positioned within that structure, not rushing, not vanishing, but located, like coordinates in space-time. The sense of flow you experience arises from entropy increasing, from neural processes encoding memory in one temporal direction, from thermodynamic gradients that distinguish earlier states from later ones. But beneath that psychological arrow, the equations remain largely symmetric. The space-time manifold remains complete. Your present awareness is not a knife edge dividing existence from non-existence. It is a local condition, defined by your frame, your motion, your gravitational environment. If you were traveling near the speed of light, your proper time would accumulate more slowly. If you were near a massive body, your clock would tick at a different rate, yet your world line would still be continuous, still coherent, still embedded in geometry. The universe does not hurry. It does not rush toward tomorrow. Tomorrow is a coordinate, just as yesterday is. Relativity suggests that past and future are not erased or unborn. They are parts of a structured whole. Events lie within light cones. Causality constrains influence. But existence itself is not sequential in the way intuition suggests. From this perspective, your life is not dissolving into nothing. It is extended across space-time, a complete curve, from its earliest coordinate to its latest. The block universe interpretation can feel unsettling at first, yet it does not remove meaning. It reframes it. Meaning arises locally, within conscious experience, within memory, within anticipation. Physics describes the structure, but experience describes traversal. Even if the traversal is not fundamental, the curvature of space-time remains real. Gravitational fields shape proper time. Light follows null geodesics. Mass energy determines curvature through Einstein's field equations. The geometry is precise, and within it, everything that occurs is woven consistently. The quiet revolution did not deny the existence of time. It clarified its dependence. It showed that time is inseparable from space. That measurement depends on motion. That simultaneity depends on frame. That gravity influences duration. That entropy gives direction to experience. And that deeper quantum descriptions may not include time as a fundamental parameter at all. These insights do not destabilize reality. They deepen it. You are not adrift in a flowing current. You are embedded in structure. Your awareness occupies a moving point along your world line. But the line itself is complete within space-time. This realization does not require urgency. There is no need to outrun the future. No need to cling to the past. Both are coordinates. Both are part of the manifold. As you rest now, your present frame defines your slice through space-time. Another observer moving differently would define another slice. Yet the space-time interval between events remains invariant, unchanged. This invariance is the anchor, the calm beneath transformation. Light cones preserve causality. Mass curves geometry. Entropy distinguishes direction. Quantum correlations encode structure. And within this ordered architecture, consciousness unfolds gently, moment by moment. Even if the moments are coordinates, the experience remains real. It is local, contextual, emergent, but not illusory. The revolution was quiet because the cosmos did not fracture. It simply revealed deeper symmetry, a deeper stillness. What appears as motion is orientation within space-time. What appears as passing is accumulation of proper time along a world line. What appears as loss is change in relational configuration. The geometry holds everything, without strain, without urgency. You are not racing against a vanishing present. You are participating in a structured continuum. Your memories correspond to earlier coordinates. Your expectations correspond to later ones. And your awareness marks the intersection of cognition and geometry. The universe does not tick like a universal clock. It curves, it relates, it transforms under motion and gravity, yet it remains internally consistent. This consistency is profoundly gentle. There is no chaos in the equations, no arbitrary drift, only transformation under invariant principles. And within that coherence, there is space for wonder, without anxiety, curiosity without haste. Time is not what you once thought. It is richer, more subtle, less like a river, more like a landscape you traverse, while simultaneously being part of its structure. As you settle into rest, imagine your world line extending quietly, backward to early coordinates, forward to later ones, all embedded in curvature, all woven into spacetime, nothing rushing, nothing collapsing, only geometry, holding every event with equal consistency. You are not outside this structure, you are a pattern within it, a localized configuration of matter and energy, following geodesics, accumulating proper time, encoding entropy gradients, participating in the universe's unfolding correlations. And yet, within that vastness, there is calm, because the geometry does not hurry, it simply is. And within that still architecture, you can rest, not against the flow of time, but within the structure that gives time meaning. The quiet revolution did not end with disruption, it ended with clarity. Time did not disappear, it transformed into something deeper, more unified, more serene. And now, within that understanding, there is nothing to chase, only awareness tracing its path within the infinite calm.